Right now, you're hurtling through space at over 500,000 miles per hour. You can't feel it. You never have. But every second, you and everything you've ever known are being dragged in a massive circle around something 4 million times heavier than the Sun, a supermassive black hole sitting at the heart of our galaxy. It takes 230 million years to complete just one lap. Dinosaurs roamed the Earth the last time we were on this side of the Milky Way. And the craziest part, we only just figured out where we actually are. If mind-bending cosmic secrets keep you up at night, smash that like button and subscribe, because this is the story of the galaxy that built us, the one we're trapped inside, and the one we almost never understood. Prepare yourselves. We begin. Before cities swallowed the darkness, before electric lights turned night into a pale shadow of day, every human who ever lived could look up and see it, a river of light stretched across the heavens, a pale glowing band that arced from horizon to horizon like a ghostly bridge between worlds. It was always there, constant and mysterious, weaving through the stars with an otherworldly glow that seemed to pulse with secrets. People everywhere saw it when the nights were clear and the moon was dark. Some thought it was smoke rising from distant fires. Others believed it was a river flowing through the sky, a celestial waterway that carried the souls of the dead to their final rest. Many saw it as the path walked by gods, a trail of light left behind by divine footsteps. This was the Milky Way, though for thousands of years no one called it that, and no one knew what it truly was. In those ancient times, humanity had no tools to measure the distance to the stars, no way to calculate the speed of light, no understanding that the universe stretched far beyond the vault of heaven they could see. All they had were their eyes, their wonder, and their stories. The ancient Greeks, who were among the first civilizations to document the stars and give them names, saw the Milky Way as a cosmic accident born from the drama of their gods. One of the most enduring legends tells of the goddess Hera and the infant Heracles, a child born from Zeus, an immortal woman. As the story goes, Zeus wanted his half-mortal son to gain divine powers, so he brought the baby to Hera while she slept and placed him at her breast. When Hera woke and realized she was nursing a child born of her husband's infidelity, she pulled away in shock and anger. Her divine milk spilled across the darkness, splashing into the heavens and forming the glowing band that mortals would see for generations to come. The Greeks called it Galaxias Kyklo, which translates to the Milky Circle. From that phrase came the word we still use today for vast collections of stars spanning the cosmos, galaxy. It's a term rooted not in science, but in myth, in the image of milk spilled by a betrayed goddess. Another version of the Greek myth says that Heracles was abandoned in the woods by his mortal parents, and the goddess Athena found him and brought him to Hera, asking her to nurse the child without revealing who he was. Hera agreed, but when Heracles bit down too hard, she pushed him away in pain. And again the milk sprayed out, forming the celestial band. These stories were more than entertainment. They were attempts to make sense of something that defied explanation, to give meaning to the unexplainable glow that hung in the night. Across the world in ancient China, astronomers kept detailed records of the stars for centuries, tracking their movements and documenting celestial events with a precision that would not be matched in Europe for over 1,000 years. The Chinese had their own name for the Milky Way. They called it the Silver River, a shimmering waterway that flowed through the heavens. To them, the band of light was not spilled milk, but a cosmic stream that separated lovers and dictated the rhythms of the universe. One of the most beloved stories tied to the Silver River is the legend of the Weaver Girl and the Cowherd. According to the tale, the Weaver Girl was a celestial being, skilled in the art of weaving clouds and making the garments of the gods. She fell in love with a mortal cowherd, and the two married in secret. But their love angered the gods, who believed that immortals should not mix with mortals. As punishment, the lovers were separated and placed on opposite sides of the Silver River. forbidden to ever touch again. However, once a year, on the 7th day of the 7th lunar month, a bridge of magpies would form across the sky, allowing the two lovers to meet for a single night. This story is still remembered today in the Qixi Festival, sometimes called Chinese Valentine's Day, celebrated across China and East Asia. The stars that represent the lovers, Vega and Altair, still shine on opposite sides of the Milky Way, their positions in the sky shifting with the seasons, just as the ancient stories described. Further west, in the lands of Mesopotamia, where civilization itself was born, the ancient Babylonians had their own interpretation of the glowing band. In Babylonian culture, the sky was not just a backdrop for the earth, but a reflection of it, a cosmic mirror where the events of heaven and earth were intertwined. The Babylonians believed the Milky Way was the tale of Tiamat, the great sky dragon of primordial chaos. According to the epic poem Enuma Elish, Tiamat was a goddess of the salt waters, a monstrous dragon who fought against the younger gods. When the god Marduk defeated her in battle, he split her body in two. One half became the earth, and the other half became the sky. Her severed tail, they said, was flung into the heavens, where it became the shimmering band of light that stretched across the darkness. Some Babylonians also saw the Milky Way as a celestial river, a reflection of the Tigris or Euphrates carried into the stars. They believed the heavens mirrored the earth, so it made sense that if there were rivers below, there would be rivers above. These stories were not idle tales. They were deeply tied to Babylonian religion, astrology, and their understanding of fate. The movements of the stars and planets were seen as omens, messages from the gods about the future of kings and kingdoms. In Africa, the interpretations of the Milky Way varied by region, but many cultures saw it as a spine or a path. Among the San people of southern Africa, also known as Bushmen, the Milky Way was described as the backbone of the night, a structure that held up the sky and kept the heavens from collapsing. Other San stories described it as the dust kicked up by travelers walking along the path to the afterlife. When people died, their souls would journey along this glowing road, and the light came from the fires they carried to guide their way. It was a comforting image, the idea that the dead were not lost, but walking together on a path that could still be seen by the living. In parts of West Africa, the Milky Way was known by similar names, often tied to ideas of support, structure, or passage. The phrase backbone of night would later inspire a modern documentary on African astronomy and indigenous star knowledge, highlighting how these ancient stories carried scientific insight wrapped in metaphor. In Northern Europe, the Norse people, known for their sagas of gods and warriors, also had stories about the Milky Way. While their myths are better remembered for tales of Thor, Odin, and the apocalyptic Ragnarok, they also spoke of the sky as a place filled with meaning. Some scholars believe the Norse may have seen the Milky Way as Bifrost, the rainbow bridge that connected Midgard, the world of humans, to Asgard, the realm of the gods. It was a shimmering path that only the gods and the souls of the honored dead could walk. The bridge was said to be guarded by the god Heimdall, who watched for any sign of the giants, who would one day storm across it and bring about the end of the world. Whether the Milky Way was truly Bifrost or another celestial road in Norse cosmology is debated, but the connection between the sky and divine passage was clear. Across the ocean, the indigenous peoples of the Americas developed their own rich traditions of sky watching and storytelling. The Inca of South America had a particularly unique way of seeing the Milky Way. Unlike many cultures that focused on the bright stars, the Inca paid close attention to the dark patches within the Milky Way, the regions where thick clouds of dust blocked the light of stars behind them. These dark shapes, which modern astronomers call dark nebulae, were not seen as empty spaces, but as celestial animals. The Inca saw a llama, a fox, a serpent, and other creatures moving through the sky. These animals were real to them, as important as the stars themselves. The Inca watched the dark shapes shift through the seasons, using their movements as signs for planting, harvest, and ceremony. The Milky Way was not just a river of light, but a living landscape filled with beings that connected the heavens to the earth. The Lakota people of the Great Plains saw the Milky Way as the spirit path, a road taken by souls after death. When someone died, their spirit would travel along this glowing trail to reach the afterlife. It was a journey that could be seen by the living, a reminder that death was not an ending, but a passage to another place. Other Native American groups had their own interpretations. The Cherokee told a story of a dog that stole cornmeal and ran across the sky, scattering it as he fled. The scattered meal became the Milky Way, a permanent reminder of the theft. It was a simple story, one that children could understand, but it also carried deeper meaning about consequences and the marks left by actions. Even in regions where writing had not yet developed, oral traditions kept these ideas alive, passed down from generation to generation through stories, songs, and ceremonies. The Aboriginal Australians, whose cultures stretch back tens of thousands of years, had remarkably detailed knowledge of the sky. The Yolngu people of northern Australia saw the Milky Way as a canoe carrying ancestral beings across the sky. The shimmering light, they said, was the reflection of their fires on the surface of the water. The stars and the dark spaces between them told stories of creation, law, and the land itself. These stories were not just myths. They were maps, calendars, and moral lessons all wrapped in the stars. They guided travelers across vast deserts, marked the seasons for hunting and gathering, and taught young people the values and history of their people. The sky was a living text, and the Milky Way was one of its most important chapters. Despite the incredible diversity of these stories, they all share something in common. Every culture that looked up and saw the Milky Way felt something deep and powerful. They didn't know that what they were seeing was the edge-on view of a massive spiral galaxy, a disk of hundreds of billions of stars stretching across 100,000 light-years. They didn't know that the faint glow came from stars so distant that their light had traveled for thousands of years to reach human eyes. They didn't know that the dark patches were clouds of gas and dust, where new stars were being born. But what they did know, what they could feel in their bones, was awe. They knew that the Milky Way was important, that it mattered, that it connected them to something larger than themselves. And from that awe, from that deep sense of wonder and the need to understand, they built the foundations of curiosity that would one day lead to science. These ancient people were the first astronomers, the first cosmologists, the first humans to ask the question that would drive all future exploration. What is that light in the sky, and what does it mean for us? They answered with stories, with gods and dragons and rivers and roads. They were wrong about the details, but they were right about the importance. The Milky Way was not just a streak of light, it was home. It was mystery. It was the canvas on which humanity painted its deepest questions about existence and meaning. And while the myths would eventually give way to telescopes and mathematics, the sense of wonder that created those myths would never fade. It would only grow stronger as humanity began to learn the truth about the galaxy that built them, the one they were trapped inside, and the one they almost never understood.
救我救我
For a very long time, humanity believed that the ground beneath their feet was the center of everything, the immovable foundation around which all creation spun. It was more than just a scientific belief. It was common sense. When you stood outside and watched the sky, the sun rose in the east, climbed overhead, and set in the west. The moon traced its arc through the darkness. The stars wheeled in perfect circles around the pole, never changing their patterns, always returning to the same positions night after night. Nothing about the earth seemed to move. You could jump and land in the same spot. You could throw a stone straight up, and it would fall back down into your hand. If the earth were spinning, wouldn't everything fly off? Wouldn't we feel the motion? It seemed obvious that the earth was still, and that everything in the heavens revolved around us. This idea, known as the geocentric model, was supported by the greatest minds of the ancient world. The Greek philosopher Aristotle, who lived more than 300 years before the birth of Christ, constructed an entire cosmology based on the belief that the Earth was at the center of the universe. He taught that the heavens were perfect, unchanging, and eternal. The Earth, by contrast, was the realm of change, decay, and imperfection. Everything had its natural place, and the Earth's place was at the center. Heavy things fell because they sought the center. Light things rose because they moved away from it. It was a system that made intuitive sense, and it dominated Western thought for centuries. Then came Claudius Ptolemy, an astronomer and mathematician who lived in Alexandria, Egypt. In the 2nd century AD, Ptolemy built on Aristotle's ideas and created a detailed mathematical model of the geocentric universe. In his work, known as the Almagest, he described how the planets, sun, moon, and stars all moved around the Earth in perfect circles. But there was a problem. The planets didn't move in simple circles. Sometimes they appeared to slow down, stop, move backward in the sky, a phenomenon called retrograde motion, and then resume their forward journey. To explain this bizarre behavior, Ptolemy added complexity to his model. He proposed that planets moved in small circles called epicycles, while those small circles moved along larger circles, called deferents. It was a system of circles within circles, a cosmic clockwork that required constant adjustments and tweaking to match observations. But it worked, at least well enough to predict the positions of the planets with reasonable accuracy. For over 1,000 years, Ptolemy's model was accepted as fact, taught in universities, supported by the Church, and woven into the fabric of European thought. The Catholic Church embraced the geocentric model because it aligned with certain interpretations of Scripture. The Bible spoke of the sun standing still in the sky during the Battle of Joshua, of the earth being set on firm foundations that could not be moved. To suggest that the earth moved was not only scientifically wrong, it was potentially heretical, a challenge to the divine order of creation. Questioning the structure of the heavens was dangerous, and those who did so risked not just ridicule, but persecution. But then, in the early 1500s, a quiet revolution began. Nicholas Copernicus, a Polish mathematician and astronomer, started to wonder if the entire system was wrong. Born on February 14, 1473, in the city of Turin, Copernicus was the son of a merchant. He studied at the University of Krakow and later traveled to Italy, where he was exposed to the intellectual ferment of the Renaissance. He studied mathematics, astronomy, medicine, and law, eventually taking a position as a canon in the Catholic Church, a role that gave him financial security and the freedom to pursue his passion for the stars. Copernicus was not a revolutionary by nature. He was cautious, meticulous, and deeply aware of the controversy his ideas might provoke. But as he studied the Ptolemaic model, he became increasingly frustrated by its complexity. The motions of the planets required too many adjustments, too many epicycles stacked on top of each other. Some planets needed multiple epicycles just to match what was observed in the sky. It felt forced, inelegant, like a theory that was being held together with patches and fixes rather than revealing a fundamental truth. Then Copernicus had a radical thought. What if the problem wasn't with the planets, but with the assumption that the Earth was the center? What if, instead, the sun was at the center and the Earth was just another planet orbiting it? This idea, known as the heliocentric model, was not entirely new. An ancient Greek astronomer named Aristarchus of Samos had proposed something similar in the 3rd century BC, but his idea had been largely ignored and forgotten. Copernicus revived it, but this time with mathematics to back it up. If the Earth orbited the sun once a year and also spun on its axis once a day, many of the strange observations suddenly made sense. The retrograde motion of the planets, for instance, was not real motion at all, but an optical illusion. When the Earth, moving faster in its inner orbit, passed a slower outer planet like Mars, that planet appeared to move backward against the stars, just like when you pass a slower car on the highway, and it seems to move backward relative to distant objects on the horizon. The heliocentric model was simpler, more elegant, and it explained the observations without needing endless layers of epicycles. But it came with a staggering implication. If the Earth moved, then humanity was not at the center of creation. We were just passengers on a spinning rock, one planet among several, orbiting an ordinary star. It was a profound demotion, a shift in perspective that would eventually change everything. Copernicus spent decades refining his model, working quietly in his observatory tower in Frombork, a small town on the coast of Poland. He made observations with the naked eye. No telescope existed yet, and he performed careful calculations to determine the distances and speeds of the planets. Around 1514, he circulated a short handwritten manuscript called the Commentariolus, or Little Commentary, to a few trusted friends. In it, he outlined the basic principles of his heliocentric system. There is no single center of the universe. The center of the Earth is not the center of the universe. The Sun is near the center, and all the planets revolve around it. The distance from the Earth to the Sun is tiny compared to the distance to the stars. The apparent daily motion of the stars is caused by the Earth's rotation. The apparent annual motion of the Sun is caused by the Earth's orbit, and the retrograde motion of the planets is caused by the Earth's motion relative to them. These ideas spread slowly through academic circles, discussed in hushed tones, debated in letters. But Copernicus hesitated to publish. He knew the firestorm that would follow. For years, colleagues urged him to release his full work, but he resisted. Finally, in 1543, just before his death, his masterpiece was published. It was titled De Revolutionibus Orbium Coelestium, or On the Revolutions of the Heavenly Spheres. According to legend, Copernicus received the first printed copy of the book on his deathbed. He had suffered a stroke, and his health was failing. Some say he regained consciousness just long enough to see the book, then died hours later, on May 24th, 1543. Whether he ever truly understood the revolution he had started is uncertain. At first, not much changed. The book was technical, dense, filled with mathematics that only a handful of astronomers could fully understand. Many readers focused on the practical aspects, using Copernicus's tables to calculate planetary positions, while ignoring or dismissing the heliocentric model itself. The idea that the Earth moved was too radical, too unsettling. But the seed had been planted. Among those who read the book carefully, doubt began to creep in. If Copernicus was right, then Aristotle was wrong. If Copernicus was right, then Ptolemy was wrong. If Copernicus was right, then the entire structure of the cosmos, as taught for over 1,000 years, was a mistake. Then came Galileo Galilei, and everything changed. Galileo was born in Pisa, Italy, in 1564, 21 years after Copernicus died. He was curious, brilliant, and unafraid of controversy. He studied mathematics and physics, and he had a talent for building instruments and conducting experiments. In 1609, Galileo heard about a new invention from the Netherlands, a device that used lenses to make distant objects appear closer. It was called a telescope. Within months, Galileo had built his own, improving the design to achieve much greater magnification. Then he did something no one had done before. He pointed it at the sky. What he saw shattered the old world view. He looked at the moon and saw mountains, valleys, and craters. The moon was not a perfect sphere, as Aristotle had claimed. It was rough, rugged, a world of its own. He looked at the sun and saw dark spots moving across its surface, sunspots that appeared and disappeared, proving that the sun was not perfect and unchanging. He looked at Venus and saw that it went through phases, just like the moon, growing from a crescent to a full disk and back again. This could only happen if Venus orbited the sun, not the Earth. Then he looked at Jupiter, and what he saw was undeniable proof that not everything orbited the Earth. Galileo discovered 4 moons circling Jupiter, tiny points of light that moved from night to night, clearly orbiting the giant planet. He called them the Medicean stars in honor of his patrons, though today we know them as the Galilean moons, Io, Europa, Ganymede, and Callisto. These moons were a miniature solar system, a clear demonstration that objects could orbit something other than the Earth. In 1610, Galileo published his findings in a short book called Sidereus Nuncius, or Starry Messenger. It caused an uproar. The telescope revealed a universe far more complex and strange than anyone had imagined. The heavens were not perfect. The Earth was not unique, and the old models could no longer explain what people were seeing with their own eyes. Galileo became a passionate advocate for the Copernican model. He wrote letters, gave lectures, and engaged in public debates. He argued that the evidence from the telescope supported the idea that the Earth moved around the Sun, but this brought him into direct conflict with the Catholic Church. In 1616, the Church officially declared that the heliocentric theory was contrary to Scripture. Copernicus's book was placed on the Index of Forbidden Books, and Galileo was warned not to teach or defend the idea that the Earth moved. For a while, Galileo stayed quiet, but in 1632, he published a book called Dialogue concerning the two chief world systems. It was written as a conversation between three characters, one defending the Ptolemaic system, one defending the Copernican system, and one acting as a neutral observer. Though Galileo tried to present both sides, it was clear where his sympathies lay. The character defending the geocentric model was named Simplicio, a name that suggested foolishness, and his arguments were systematically dismantled. The Pope, Urban VIII, who had once been Galileo's friend, was furious. He felt betrayed and humiliated. Galileo was summoned to Rome to face the Inquisition. In 1633, at the age of 69, Galileo stood trial. He was accused of heresy for teaching that the Earth moved. Under threat of torture, he recanted, publicly stating that he had been wrong and that the Earth did not move. He was sentenced to house arrest for the rest of his life. Legend says that after his trial, as he left the courtroom, he muttered under his breath, "And yet it moves." Whether he actually said this is debated, but the sentiment captures the spirit of the moment. The truth could not be suppressed forever. While Galileo was silenced, others continued the work. Johannes Kepler, a German astronomer, took the heliocentric model and refined it even further. Using detailed observations made by the Danish astronomer Tycho Brahe, Kepler discovered that the planets did not move in perfect circles, but in ellipses, oval-shaped orbits with the Sun at one focus. He published this discovery in 1609 in a book called Astronomy Nova, or New Astronomy. Kepler also discovered that planets moved faster when they were closer to the Sun and slower when they were farther away, a relationship now known as Kepler's second law. These discoveries made the heliocentric model not just simpler, but more accurate than anything that had come before. Then, in 1687, Isaac Newton published his Principia Mathematica, one of the most important scientific works ever written. In it, Newton described the law of universal gravitation, showing that every object in the universe attracts every other object with a force that depends on their masses and the distance between them. Gravity explained why the planets orbited the Sun, why the Moon orbited the Earth, and why objects fell to the ground. It was the same force acting everywhere, from an apple falling from a tree to the motion of the planets across the sky. Newton's laws turned the heliocentric model from a controversial hypothesis into a proven fact. The solar system was no longer a mystery. It was a machine governed by mathematics, predictable, elegant, and beautiful. But even as the heliocentric model triumphed, a deeper question remained. If the Earth was just one planet, orbiting one star, what were all the other stars? Were they suns too? And if so, did they have planets of their own? The answers to these questions would take centuries to uncover, but the process had begun. The Copernican revolution did more than change our understanding of the solar system. It changed our understanding of ourselves. We were no longer the center of creation. We were part of something much larger, a universe that stretched far beyond what anyone had imagined. and the glowing band of light in the night sky, the Milky Way, would soon reveal itself to be not just a collection of stars but a galaxy, a vast spiral of hundreds of billions of suns, one of which was ours. By the time telescopes became powerful enough to show that the Milky Way was made of stars, millions upon millions of them, a far bigger mystery had already taken root. What was the shape of it all? What was the true form of this vast collection of stars we lived inside? The question turned out to be one of the most difficult challenges in astronomy, not because the tools were missing, but because of where we were standing. We were trapped inside the very thing we were trying to map, like trying to sketch the layout of a massive forest while standing somewhere deep in the middle of it, surrounded by trees. You can see the trunks and branches around you, count them, measure them, but the full pattern, the shape of the whole forest, remains hidden, no matter how carefully you look. That was the problem astronomers faced when they tried to understand the Milky Way. There was another obstacle too, one that would take centuries to overcome. Between the stars, filling the vast empty spaces, were thick clouds of gas and dust. These clouds were cold, dark, and dense, and they blocked visible light. Even if a distant part of the galaxy was out there glowing with the light of a billion suns, much of that light would never make it to Earth because it was swallowed by the dark curtains of interstellar dust. For years, this made progress agonizingly slow. Early astronomers counted stars and tried to map the sky, hoping to figure out where the galaxy was thickest, where it was brightest, and whether we were sitting near the center or off to one side. In the late 1700s, the astronomer William Herschel, working with his sister Caroline, attempted just that. Using a large homemade telescope, Herschel systematically surveyed the sky, counting stars in different directions, and trying to determine the overall shape of the Milky Way. He proposed that the galaxy might be shaped like a flattened disk, thicker in some directions than others. His maps were rough and based on assumptions that would later prove incorrect, but they were a start. Without a way to see through the dust, his map was more of an educated guess than a true picture of the galaxy. Everything changed when scientists learned to look beyond visible light. Light, it turned out, was not a single thing, but a spectrum, a range of electromagnetic waves that stretched far beyond what human eyes could detect. There were wavelengths shorter than visible light, like ultraviolet and X-rays, and wavelengths that were longer, like infrared and radio waves. These longer wavelengths had a special ability. They could pass through dust. Infrared light sits just beyond the red end of the visible spectrum, emitted by warm objects like stars hidden behind thick clouds. Radio waves are even longer, stretching from millimeters to meters in length. They can travel through thick clouds of gas and dust almost without being disturbed at all. These invisible signals held the key to uncovering the Milky Way's true shape, and in the mid-20th century, astronomers finally learned how to listen to them. Radio astronomy was born not from a deliberate search for new technology, but from an accidental discovery. In 1931, an engineer named Carl Jansky, working for Bell Telephone Laboratories, was trying to track down the source of static that interfered with radio communications. He built a large rotating antenna and discovered that some of the static was coming from the sky, specifically from the direction of the center of the Milky Way. It was the first detection of radio waves from space, and it opened an entirely new window into the universe. At first, the discovery was mostly ignored. Radio astronomy seemed like a curiosity, not a serious tool for studying the stars. But during and after World War II, advances in radar technology gave astronomers the tools they needed to build powerful radio telescopes. These instruments didn't use glass lenses or mirrors like optical telescopes. Instead, they used giant metal dishes to collect faint radio signals coming from space, focusing them onto sensitive receivers that could detect even the weakest emissions. One of the first big breakthroughs came from studying hydrogen, the most common element in the universe. In the cold depths of space, most of the gas between stars is made of hydrogen atoms. These atoms are incredibly simple, just one proton and one electron, but they have a quirk. When the electron in a hydrogen atom flips its internal spin, the atom releases a tiny burst of energy in the form of a radio wave with a very specific wavelength, 21 centimeters long. This signal, though incredibly faint, can be picked up by radio telescopes, and because it comes from hydrogen gas, it reveals where that gas is located in the galaxy. In the 1950s, astronomers started using this 21-centimeter hydrogen line to map the Milky Way. As they listened to the radio waves coming from different directions, they noticed something remarkable. The hydrogen wasn't spread out evenly. It was gathered in long curved paths, structures that wrapped around the center of the galaxy like the arms of a giant pinwheel. These were spiral arms, regions where gas and dust were concentrated, where new stars were being born, and where the galaxy's structure was most clearly defined. It was one of the first clear signs that the Milky Way was a spiral galaxy, not a simple round cloud of stars, but a structured system with arms that curled outward from a dense central region. The discovery was revolutionary. For the first time, astronomers could see the architecture of the galaxy they lived in, not with their eyes but with radio waves that pierced through the dust and revealed the hidden framework underneath. Infrared telescopes were the next big step. In the 1980s and 1990s, space agencies launched missions like the Infrared Astronomical Satellite, known as IRAS, and later the Spitzer Space Telescope. These observatories orbited above Earth's atmosphere, which blocks much of the infrared light from space, and from that vantage point, they could see the heat glow of stars and gas that visible light telescopes could not. With these tools, astronomers were able to peer into the dusty core of the Milky Way for the first time. What they found was a crowded, complex region full of old red stars, dense star clusters, and strange elongated structures. At the heart of it all was a bar-shaped cluster of stars stretching through the center, a feature that meant our galaxy was not just a simple spiral, but a barred spiral, a form seen in many other galaxies across the universe. The bar was a revelation. It showed that the inner part of the Milky Way was not symmetric, but stretched out, rotating like a cosmic backbone that influenced the motion of everything around it. The bar helped drive gas inward toward the center, feeding star formation and funneling material toward the supermassive black hole that lurked at the galaxy's core. Infrared and radio maps started to overlap, and astronomers began combining data from multiple wavelengths to build a more complete picture. The Milky Way, they realized, was a thin disk with curved spiral arms, a thick bulge in the middle shaped like a bar, and a surrounding halo made of older stars and mysterious dark matter. It was a galaxy much like many others, but to us, it was home. Still, even with this new understanding, mapping the Milky Way remained difficult. Unlike distant galaxies that we can see as whole objects in the sky, we can't look at our galaxy from the outside. We're stuck inside it, and every map of the Milky Way is a reconstruction, pieced together from signals coming in from all directions, analyzed, modeled, and translated into images that show what the galaxy might look like if we could somehow step outside and view it from above. To make these maps more accurate, astronomers used another powerful tool, the Doppler shift. Just like the sound of a passing train changes pitch as it moves toward you and then away from you, light and radio waves also shift, depending on whether the source is moving toward or away from us. By measuring the shift in the 21-centimeter hydrogen line, scientists could figure out how gas clouds in the galaxy were moving, how fast they were rotating, and in which direction. These movements helped reveal where the spiral arms were located and how they rotated around the center. The spiral arms themselves are not solid structures. They're not like the arms of a spinning wheel, permanently attached and rotating as one piece. Instead, they're density waves, regions where gas and dust pile up temporarily as stars and clouds move through them. When gas enters a spiral arm, it gets compressed, triggering the collapse of clouds and the birth of new stars. These young, hot blue stars light up the spiral arms, making them visible and giving the galaxy its characteristic pinwheel appearance. But the stars don't stay in the arms forever. They move through them, like cars moving through a traffic jam on a highway. The traffic jam stays in place while the cars pass through. All of this work has painted a clearer picture of the Milky Way than anyone in history could have imagined. We now believe the galaxy has four main spiral arms: the Perseus arm, the Scutum Centaurus arm, the Norma arm, and the Sagittarius arm, though some are more well-defined than others, and there are smaller branches and spurs that connect them. Our solar system sits in one of these smaller branches, a structure known as the Orion arm or Orion Spur, a short segment of stars and gas that runs between the larger Perseus and Sagittarius arms. From inside, the Milky Way still looks like a faint streak of stars and dust, the same pale band that ancient peoples saw and wove into their myths. But thanks to the patient work of many scientists and engineers over decades, we've pulled back the curtain. We now know that we live in a majestic spinning city of stars, a barred spiral galaxy with curved arms stretching across roughly 100,000 light-years, filled with hundreds of billions of stars, vast clouds of gas and dust, and regions where new stars are being born even now. Even now, the picture is not complete. Parts of the galaxy remain unmapped, hidden behind thicker clouds or confused by overlapping signals from multiple regions. The exact number of spiral arms is still debated. Some models suggest there are 4 major arms. Others propose 2 major arms, with several smaller ones. The structure of the bar at the center is still being refined, and new discoveries continue to reshape our understanding. But every year, new instruments and missions continue the work. Space-based observatories like the Gaia satellite are mapping the positions and motions of over 1 billion stars with unprecedented precision, creating a 3-dimensional map of the galaxy that reveals not just where stars are, but how they're moving. Ground-based radio arrays are listening to the whispers of hydrogen gas across vast distances, tracing the invisible skeleton of the galaxy. And detailed computer models are simulating how the Milky Way grew over billions of years, testing theories about how spiral arms form, how the bar developed, and what role dark matter plays in holding everything together. What once seemed like a hazy trail of stars, a mystery wrapped in myth and wonder, has become a vast spiral system, slowly revealing itself piece by piece. The Milky Way is still unfolding before our eyes, still offering new surprises, still reminding us of how far we've come from the days when people thought the stars circled the Earth. Now we know we are the ones who move, spinning quietly inside a galaxy that is alive with motion, filled with structure, shaped by forces we're only beginning to understand. And the most humbling part of it all is that this galaxy, vast as it is, containing hundreds of billions of stars and stretching across distances that light takes 100,000 years to cross, is just one galaxy among trillions in the observable universe. The Milky Way is our home, but it's also a reminder of how small we are and how much there is left to discover. From Earth, the sky looks the same in every direction, a seamless dome of stars scattered across the darkness, and for most of human history, there was no reason to think we were anywhere special or anywhere strange within that cosmic landscape. The galaxy didn't come with a map, no signs pointing toward the center or labels marking where we stood, so scientists had to figure it out the hard way, piece by piece, using nothing but starlight and mathematics. The first serious attempts to map our location began in the 1700s, when astronomers like William and Caroline Herschel tried to count stars in different parts of the sky. The goal was simple and elegant. If we were near the center of the galaxy, we should see roughly the same number of stars in all directions. If we were off to one side, then one part of the sky should be more crowded with stars than the others. The Herschels used a large homemade telescope and painstakingly counted stars, section by section, building up a rough map of the Milky Way. Their early maps suggested that we weren't in the center, but they were limited by the technology of their time, and the fact that thick clouds of interstellar dust blocked their view of distant regions. Still, it was enough to hint that the Sun and Earth weren't sitting at the heart of creation. The breakthrough came much later, in the early 20th century, when astronomers discovered a type of star that could be used as a cosmic measuring stick. These stars were called Cepheid variables, and they had a remarkable property. They pulsed, growing brighter and dimmer in a regular rhythm, and the length of that rhythm was directly tied to how bright the star truly was. If you measured how long it took a Cepheid to pulse, you could calculate its actual luminosity, its true brightness. Then, by comparing that to how bright it appeared from Earth, you could figure out how far away it must be. It was like looking at a light bulb across a dark field. If you know the bulb is 100 watts, you can estimate how far away it is by how dim it looks. This method revolutionized astronomy because for the first time, astronomers had a reliable way to measure distances to faraway objects. In the early 1900s, a Harvard astronomer named Henrietta Swan Leavitt studied thousands of Cepheid variables in the Small Magellanic Cloud, a satellite galaxy of the Milky Way, and she discovered the relationship between their pulsation period and their luminosity. Her work laid the foundation for everything that followed. Using Cepheid variables and other distance measurement techniques, astronomers began to map the structure of the Milky Way with increasing precision. One of the key figures in this effort was Harlow Shapley, who in the 1910s studied globular clusters, dense spherical collections of ancient stars that orbited the galaxy. Shapley measured the distances to these clusters and noticed that they were not centered around the Sun. Instead, they were distributed in a lopsided pattern, concentrated in one part of the sky, toward the constellation Sagittarius. This told him something profound. The center of the galaxy was not where we were, but somewhere in the direction of Sagittarius, tens of thousands of light years away. Shapley's work was groundbreaking. Though his initial estimates of the galaxy's size turned out to be too large because he didn't account for the dimming effect of interstellar dust, later studies refined the numbers, and by the mid-20th century, astronomers had settled on a figure that has held up remarkably well. The solar system sits about 26,000 light-years from the center of the Milky Way. That's roughly halfway from the dense hub of stars and gas at the galactic core to the outer edge of the disk, which stretches to about 100,000 light-years across. We're not at the center, not even close, but we're also not at the edge. We're in the suburbs, a quiet middle-distance region where the density of stars is moderate and the pace of life is relatively calm. But knowing our distance from the center was only part of the puzzle. Scientists also wanted to know what part of the galaxy we were in. The Milky Way, after all, has structure. It has spiral arms, long curving lanes of gas, dust and stars that wind outward from the center, like the arms of a giant pinwheel. These arms are where most of the action happens. Regions filled with nebulae, young blue stars, and active star formation. Mapping these arms from the inside was incredibly difficult, but radio astronomy made it possible. By tracking the emissions from hydrogen gas, astronomers in the 1950s and 60s began to trace the spiral structure of the Milky Way. What they found was that our solar system doesn't sit right on one of the big main arms. Instead, it lies in a smaller structure called the Orion Arm, also known as the Orion Spur, a short narrow bridge of stars and gas that runs between two of the larger spiral arms, the Sagittarius arm on the inner side and the Perseus arm on the outer side. It's not a major highway of star formation, not one of the galaxy's grand sweeping arms, but it's still home to millions of stars, including our Sun. Think of it as a side street off a main boulevard, quieter, less crowded, but still part of the city. The Milky Way is not a static object. It spins. Everything inside it, including our solar system, moves in a vast cosmic dance. Stars orbit the galactic center, the way planets orbit the Sun, though on a much grander scale and at speeds that dwarf anything we experience on Earth. Our Sun, along with all the planets that follow it, makes a full loop around the galaxy about once every 230 million years. This movement is called the galactic orbit, and our speed is staggering, roughly 828,000 kilometers per hour, or about 514,000 miles per hour. That motion is so smooth and constant that we can't feel it. There's no jolt, no sensation of movement, because everything around us, the planets, the stars, the gas clouds, is moving with us. But by measuring the light from stars and how it shifts, astronomers can detect how fast things are moving. This technique, based on the Doppler effect, the same principle that makes a passing siren change pitch, allows scientists to map the motion of stars and gas clouds across the galaxy. By looking at how different parts of the Milky Way rotate, scientists discovered something strange. The speed of rotation didn't drop off the way it should have if only visible matter, stars and gas, were involved. According to the laws of gravity, objects farther from the center of a galaxy should move more slowly, just like planets in our solar system. Mercury, close to the Sun, whips around quickly. Neptune, far out on the edge, moves much more slowly, but in the Milky Way, stars near the edge were moving almost as fast as stars closer to the center. This didn't make sense unless there was something else, something invisible, adding extra mass and gravity to the galaxy. That something was dark matter, a mysterious substance that doesn't emit light but exerts a powerful gravitational pull. The discovery of dark matter revolutionized our understanding of galaxies, but it also helped pin down our exact position. Rotation models showed how our solar system moves along its galactic path, how it fits into the larger structure of the spiral arms, and how the galaxy's gravity holds everything together. Another tool in finding our place came from pulsars, the collapsed remnants of massive stars that exploded as supernovae. Pulsars spin rapidly, sometimes hundreds of times per second, and they emit beams of radio waves that sweep across space like the beam of a lighthouse. Because each pulsar has a unique pattern of pulses, they can be used to measure distances and map locations with extreme precision. Some scientists have compared pulsars to a cosmic GPS system. By timing the signals from several pulsars, you can triangulate your position in the galaxy. This technique was famously used on the Voyager spacecraft, which carried a golden record with a map showing Earth's location relative to 14 pulsars. As more pulsars were discovered and cataloged, they helped confirm the structure of the Milky Way's spiral arms and the motion of objects within them. They added another layer of detail to the growing map that showed where we live, not just our star but its neighborhood, its street, its place within the spinning disk of the galaxy. Other nearby stars have also helped guide our understanding. For example, stars that are part of the same moving group as the Sun, known as the local standard of rest, give us clues about how our area of the galaxy behaves. By comparing their speeds and directions, astronomers get a sense of how the solar system fits into the larger traffic flow of stars orbiting the center. There are stars that move faster than us, stars that move slower, and stars that drift in slightly different directions. All of this motion reveals the dynamic, ever-changing nature of the galaxy. In recent years, the European Space Agency's Gaia satellite has taken this work to an entirely new level. Launched in 2013, Gaia has been mapping the positions and motions of over 1 billion stars with unprecedented precision. It measures not just where stars are, but how they're moving, how far away they are, and what they're made of. The data from Gaia is creating a three-dimensional map of the Milky Way that reveals the galaxy in stunning detail, showing not just the spiral arms, but the ripples, waves, and disturbances left behind by ancient collisions with smaller galaxies. Gaia has confirmed that we live in the Orion Spur, about 26,000 light-years from the galactic center, moving at over 500,000 miles per hour in a slow, steady orbit that takes us around the galaxy once every 230 million years. That means The last time our solar system was in this part of the galaxy, dinosaurs had not yet appeared on Earth. The continents were arranged differently, the climate was warmer, and life was still dominated by simple organisms. One full galactic year from now, if humanity or whatever comes after us is still around, the sun will have completed another lap, and the galaxy will have changed in ways we can barely imagine. Stars will have been born and died, spiral arms will have shifted, and the Milky Way will be a little older, a little more evolved. Today, thanks to centuries of patient observation, mathematical modeling, and technological innovation, we can point to a location on a map of the Milky Way and say with confidence, there we are. Not at the center, but tucked partway out in a quiet arm between giants, a small yellow star with a family of planets, one of which harbors life. We orbit with hundreds of billions of other stars, all of them moving through a galaxy that is both familiar and still full of mysteries. A galaxy that is home to wonders we're only beginning to understand. And perhaps most remarkably, our location may be one of the reasons life was able to develop here at all. The galactic center is a violent place, crowded with stars, flooded with radiation, and dominated by a supermassive black hole. The outer edges of the galaxy are quieter, but also poorer in heavy elements, the building blocks of planets and life. Our position, halfway out in a moderate density region, may be a kind of galactic Goldilocks zone, not too close to the chaos of the center, not too far from the resources needed to build worlds. It's a humbling thought. We're not at the center of the universe, not even close, but we're exactly where we need to be. When scientists try to measure how big the Milky Way really is, they don't just look at how wide it appears or count the stars they can see. They look at how much stuff it contains, how far out its gravitational pull reaches, and most importantly, how fast things are moving inside it. All of that helps build a more complete picture of the galaxy's true size and structure. But it also brings up one of the most baffling problems in all of modern science. Most of the Milky Way's mass isn't visible, which makes measuring the galaxy a lot more complicated and a lot stranger than it seems at first. The stars, gas, and dust we can see, all the bright spiral arms, the glowing core, the scattered star clusters around the edges, make up just a small portion of the Milky Way's total mass. If you added up all the light-emitting objects in the galaxy, every star, every planet, every glowing gas cloud, every grain of dust reflecting starlight, they would only account for about 10 to 15% of the Milky Way's total mass. The rest, the overwhelming majority, is something else entirely. Something that doesn't shine, doesn't interact with light, and can only be detected by the way it pulls on things with gravity. The first clues that something was wrong came from watching how stars move. In the early 20th century, astronomers began measuring the speeds of stars at different distances from the center of the galaxy. According to the laws of gravity, the farther you get from a central mass, the slower you should move, just like planets in our solar system. Mercury, which is close to the sun, whips around it at incredible speed, completing an orbit in just 88 days. Neptune, far out on the edge of the solar system, crawls along at a much slower pace, taking over 160 years to complete a single orbit. That's what physics predicts, and it's what we observe in planetary systems. But when astronomers tracked stars near the edges of the Milky Way, they weren't slowing down the way they should have. Stars far from the galactic center were moving almost as fast as stars much closer in. In some cases, they were moving even faster than expected. That didn't make sense. If the only mass in the galaxy was what we could see, the stars and gas and dust, then the outer stars should have been moving much more slowly. Some of them should have been moving so slowly that they would drift away from the galaxy entirely, no longer bound by its gravity. But that wasn't happening. Something was holding them in place, something with mass, something that added extra gravity and kept the outer stars whipping around at high speed. That something was called dark matter, and it turned out to be one of the most profound discoveries in the history of astronomy. Dark matter is the best explanation we have for a long list of strange observations, not just in our galaxy, but in many others across the universe. It doesn't interact with light in any way. It doesn't absorb light, doesn't reflect it, doesn't emit it. You can't see it with a telescope, no matter how powerful, but it does interact with gravity, and that's how we know it's there. In the Milky Way, dark matter seems to form a vast halo, an invisible shell that stretches far beyond the visible edge of the galaxy's disk. This dark matter halo might reach out more than 300,000 light-years from the center, wrapping around the galaxy like a cocoon, dwarfing the bright spiral structure we think of as the Milky Way. This changes everything about how we think about the size of the galaxy. If we only count the part that glows, the stars and gas clouds, we get the classic number, about 100,000 light-years across. But if we include the dark matter halo, the galaxy is much larger. Its true gravitational size could be 3 times that or more, depending on where you draw the line and how far out the Milky Way's gravity still holds on to objects and satellites. The Milky Way has many smaller satellite galaxies orbiting it, tiny systems of stars that cling to the galaxy's outer edges like moons around a planet. The most famous are the Large and Small Magellanic Clouds, 2 irregular dwarf galaxies visible from the southern hemisphere that have been known since ancient times. But there are many more, some of them barely more than faint smudges of stars discovered only in recent decades. These dwarf galaxies stay in orbit because of the Milky Way's gravitational pull. If the galaxy had less mass, they would drift away into the void. The fact that they stay so tightly bound, some of them orbiting for billions of years, is one more clue that there's a huge invisible mass holding them in place. Measuring that mass is a tricky task. You can't put the Milky Way on a scale. You can't directly observe dark matter with any instrument we've built so far. Instead, scientists use motion to estimate mass. The speed at which stars and gas clouds orbit the galaxy tells us how much gravity is acting on them. Faster speeds mean more mass. By mapping the rotation of stars at different distances from the center, astronomers can build a model of how mass is distributed throughout the galaxy. These models include both visible matter and dark matter. But the Milky Way isn't a simple flat object with evenly spaced stars. It has clumps, gaps, spiral arms, and dense clouds. It has a central bulge of older stars and a halo that isn't perfectly round. And the dark matter doesn't clump the same way normal matter does. It spreads out more evenly, forming a smooth background structure that holds everything together without forming stars or planets or anything we can directly observe. Every estimate of the galaxy's mass is built with gaps that have to be filled using mathematics, physics, theory, and comparisons with other galaxies. Despite these challenges, astronomers have come up with a rough estimate of the Milky Way's total mass. Current models suggest it holds about 1 to 1.5 trillion times the mass of our Sun. But only about 100 to 200 billion of those solar masses are real stars, the kind we can see shining in the night sky. The rest of the mass, roughly 85 to 90%, is dark matter, an enormous amount of hidden material, shaping everything we see and do within the galaxy. This dark foundation also affects how the galaxy interacts with its neighbors. The Milky Way and the Andromeda galaxy are the 2 largest members of a group of galaxies, known as the Local Group, and they're on a collision course. In about 4 billion years, the 2 galaxies will begin to merge, their stars intermixing, their gas clouds colliding, and their supermassive black holes eventually spiraling together. The outcome of that collision, how fast it happens, how violent it is, what kind of galaxy emerges afterward, depends heavily on how much dark matter each one contains. Even now, the dark matter halos of the Milky Way and Andromeda may already be brushing against each other, influencing each other's motions. That's how large and far-reaching they are. Long before the visible parts of the galaxies meet, their invisible components could already be interacting, pulling and tugging across the millions of light years that still separate them. The mystery of dark matter goes deeper than just the Milky Way. It's woven into the fabric of the entire universe. When astronomers look at clusters of galaxies, massive collections of hundreds or thousands of galaxies, bound together by gravity, they see the same pattern. The galaxies are moving too fast to be held together by the mass we can see. There must be dark matter there too, vastly more of it than visible matter. When scientists study the cosmic microwave background, the faint afterglow of the Big Bang that fills the entire universe, they find patterns in the temperature fluctuations that can only be explained if dark matter exists and makes up about 27% of the total mass energy content of the universe. Ordinary matter, the stuff that makes up stars, planets, and people, accounts for only about 5%. The rest is dark energy, an even more mysterious force that's causing the universe to expand faster and faster. But despite all this evidence, we still don't know what dark matter actually is. The leading theory is that it's made of particles, exotic subatomic particles that barely interact with ordinary matter. These particles, often called WIMPs, weakly interacting massive particles, would pass through normal matter almost as if it weren't there, streaming through planets, stars, and even our own bodies without leaving a trace. Scientists have built massive underground detectors buried deep beneath mountains to shield them from cosmic rays and other interference, hoping to catch the rare moment when a dark matter particle collides with an atom. So far, these experiments haven't found anything definitive. Other experiments are searching for dark matter in space. NASA's Fermi Gamma Ray Space Telescope has detected a mysterious glow of gamma rays coming from the center of the Milky Way, and some scientists think this could be the signature of dark matter particles colliding and annihilating each other, releasing bursts of high-energy light in the process. New simulations, published in 2025, suggest that the shape and intensity of this glow match what we would expect if dark matter near the galactic center were clumping in a flattened, egg-shaped distribution, not the perfect sphere scientists once assumed. The findings show that dark matter could indeed be behind this mysterious gamma ray excess, though it's not definitive proof. The other possibility is that the glow comes from old, rapidly spinning neutron stars called millisecond pulsars, which also emit gamma rays. Both theories are now considered essentially indistinguishable with current data, and scientists are hoping that future instruments like the Cherenkov Telescope Array, which will observe gamma rays at much higher resolution, will finally settle the debate. If the excess truly arises from dark matter collisions, it would mark the first indirect evidence that dark matter particles really exist, a discovery that would revolutionize physics and cosmology. If it turns out to be pulsars, that too would teach us something valuable about how stars age and die in the dense regions near the galactic center. Either way, the answer will bring us closer to understanding the forces that shape galaxies. In 2025, researchers also reported potential evidence of a dark matter subhalo, a smaller clump of dark matter embedded within the Milky Way's larger halo, detected by observing the way pulsars moved as they passed through a gravitational disturbance. If confirmed, it would be the first direct detection of one of these subhalos, which are predicted to exist in large numbers according to dark matter models, but have been incredibly difficult to find. The stakes are enormous. If dark matter is real and made of particles, then there's an entire hidden universe of matter all around us, invisible but ever present, shaping the motions of galaxies and the structure of the cosmos itself. If dark matter doesn't exist, then our understanding of gravity is wrong, and we need a new theory to explain why galaxies behave the way they do. Some scientists have proposed alternative theories, modifications to the laws of gravity that would eliminate the need for dark matter, but so far, none of these theories have been able to explain all the observations as well as dark matter does. The evidence keeps piling up, from the rotation of galaxies, to the motions of galaxy clusters, to the patterns in the cosmic microwave background, all pointing to the existence of this mysterious invisible substance. And so the search continues. Underground detectors keep running, space telescopes keep watching, and theorists keep building models, all in the hope of finally solving the mystery. What is dark matter? Where does it come from? Can we ever detect it directly? These are some of the biggest questions in science. And the Milky Way, our home galaxy, is one of the best places to search for answers. The hidden mass problem is not just a curiosity, it's a fundamental mystery about the nature of the universe. A reminder that even when we think we understand how things work, there are still vast unknowns lurking just beyond our reach, invisible but undeniable, shaping the cosmos in ways we're only beginning to comprehend. At the very center of the Milky Way, hidden behind thick clouds of dust and gas that block all visible light, lies something that shouldn't exist according to everything we once thought we knew about the universe. It's a region so dense, so violent, so utterly extreme, that it defies easy description. Stars packed together so tightly that they whip around in orbits that take them from the outer edges of the solar system to distances closer than Mercury orbits the Sun, all in a matter of years. Gas clouds heated to millions of degrees, glowing in X-rays and radio waves. And at the absolute center of it all, lurking in the darkness like a cosmic predator, is a supermassive black hole with a mass of roughly 4 million times that of our Sun. This beast, known as Sagittarius, a star, or Spur, a star for short, is the anchor point around which everything in the galaxy rotates, the heaviest single object in the Milky Way, and one of the most mysterious and fascinating structures in the known universe. For most of human history, we had no idea it was there. The galactic center sits about 26,000 light-years away from Earth, in the direction of the constellation Sagittarius, one of the densest and brightest regions of the Milky Way when viewed from our planet, but visible light telescopes couldn't see through the dust. It wasn't until the development of radio astronomy in the mid-20th century that scientists began to detect something strange coming from that direction. In the 1930s and 40s, radio astronomers, picking up signals from space, noticed a powerful source of radio waves coming from the center of the galaxy. As technology improved and radio telescopes became more sensitive, that source became clearer and more defined. By the 1970s, astronomers had pinpointed an incredibly compact radio source right at the galactic center, and they named it Sagittarius, a star. At first, no one knew what it was. It was too small to be a cluster of stars, too bright to be a single normal star, and too stable to be a supernova. The leading theory was that it might be a black hole, but proving that required more than just detecting radio waves. It required watching how objects near the center moved, how fast they orbited, and what kind of gravitational force was pulling on them. That's exactly what a team of astronomers set out to do in the 1990s. Using infrared telescopes, which could see through the dust, a group led by Andrea Ghez at UCLA and another led by Reinhard Genzel in Germany began tracking individual stars near the galactic center. Infrared light, with wavelengths longer than visible light, could pierce the veil of dust and reveal the crowded star field around Sagittarius, a star. What they found was astonishing. The stars near the center were moving at incredible speeds, faster than any stars had ever been observed to move. One star in particular, designated C2, became the key to unlocking the mystery. C2 is a massive blue star, much larger and brighter than our Sun, and it orbits incredibly close to Sagittarius, a star. Over the course of 16 years, astronomers watched C2 complete a full orbit, tracing an elongated ellipse that brought it screaming past the black hole at speeds approaching 3% the speed of light. At its closest approach, C2 came within about 17 light hours of Sagittarius, a star, closer to the black hole than Neptune is to our Sun. The speed and shape of C2's orbit allowed scientists to calculate the mass of the object it was orbiting. The math was undeniable. Sagittarius, a star, had to contain roughly 4 million solar masses, packed into a region smaller than the orbit of Mercury. There was no known object that could hold that much mass in such a small space, except the black hole. In 2020, Andrea Ghez and Reinhard Genzel were awarded the Nobel Prize in Physics for their decades of work, proving that a supermassive black hole sits at the center of our galaxy, But the story didn't end there. In 2022, the Event Horizon Telescope, a global network of radio telescopes working together to create an Earth-sized virtual telescope, released the first direct image of Sagittarius A star. The image showed a glowing ring of hot gas swirling around a dark central shadow, the signature of a black hole. It was the second black hole ever imaged, following the groundbreaking image of the black hole at the center of the galaxy M87, released in 2019. But Sagittarius A star is much closer to us, and seeing it confirmed what astronomers had suspected for decades. The beast at the heart of the Milky Way is real, and it's been hiding in plain sight all along. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. For a black hole with the mass of Sagittarius A star, the event horizon is about 24 million kilometers across, roughly the size of Mercury's orbit. Anything that crosses that boundary is gone forever, pulled into a singularity where the laws of physics, as we understand them, break down. But black holes don't just swallow things. They also influence everything around them. The region surrounding a black hole, called the accretion disk, is where material spirals inward, heating up to extreme temperatures as it falls. This process releases enormous amounts of energy in the form of X-rays, radio waves, and sometimes powerful jets of particles that shoot out at near light speed. Sagittarius A star, however, is surprisingly quiet. It's not actively feeding on large amounts of material, at least not right now. Compared to other supermassive black holes at the centers of other galaxies, some of which are so active they outshine every star in their galaxy combined, Sagittarius A star is almost dormant. It accretes only about 1/100,000th of a solar mass per year, a tiny trickle of gas and dust that barely registers. But that doesn't mean it's inactive. Astronomers have observed sudden flares of X-rays and infrared light from the region around Sagittarius A star, brief bursts of energy that suggest something, maybe a gas cloud or even a small asteroid, got too close and was torn apart by the black hole's gravity. These flares can brighten the region around the black hole by a factor of hundreds within minutes, then fade away just as quickly. It's a reminder that even a sleeping monster can wake up. The area immediately surrounding Sagittarius A star is one of the most extreme environments in the galaxy. Within just 1 parsec, about 3.2 light years, of the black hole, there are roughly 10 million stars packed together, dominated by red giants, but also including a significant population of massive supergiants and Wolf-Rayet stars, some of the hottest and most luminous stars in the universe. These stars were born in a burst of star formation about 1 million years ago, triggered by the unique conditions near the galactic center. How stars can form so close to a supermassive black hole is still a mystery. The intense gravitational forces and tidal effects should tear apart the gas clouds that collapse to form stars. But somehow, in this chaotic environment, stars are born anyway. Some of these stars have been caught in the black hole's gravitational grip and are doomed. Eventually, over millions or billions of years, they'll be pulled in, torn apart by tidal forces in a process called spaghettification, where the difference in gravitational pull between the near and far side of an object becomes so extreme that it stretches like taffy before being ripped to shreds. Other stars have been flung outward at incredible speeds, ejected by gravitational interactions with the black hole or with other stars. These hypervelocity stars, traveling at speeds of hundreds of kilometers per second, are racing out of the galaxy entirely, never to return. The galactic center also contains dense clouds of gas and complex structures that astronomers are still trying to understand. One of these is called the mini-spiral, a set of 3 distinct streams of hot ionized gas that appear to spiral inward towards Sagittarius A star. The mini-spiral is visible in radio wavelengths and seems to be fed by winds from massive stars in the region. Another structure, called the circumnuclear disk, is a ring-shaped cloud of gas and dust that orbits the black hole at a distance of several light years. This disk rotates around the center and may be feeding material slowly inward over time, providing the trickle of fuel that keeps Sagittarius, a star, glowing faintly. The central bar of the Milky Way, a stretched-out region of stars that extends for thousands of light years, plays a crucial role in funneling gas toward the center. The bar itself formed billions of years ago as the inner part of the galaxy became gravitationally unstable, and stars began moving in elongated orbits rather than circular ones. This bar acts like a conveyor belt, channeling gas from the outer parts of the galaxy inward toward the core. As gas flows along the bar, it loses angular momentum and spirals closer to the center, where it can fuel star formation and eventually feed the black hole. Some astronomers believe the Milky Way might have two bars, a larger outer bar and a smaller inner bar nested within it, creating a complex system of gas flows and star formation regions. The bar is also responsible for creating shock waves in the gas as it moves through the inner galaxy, piling up material and triggering bursts of star formation. One of these shock structures, called the 3 kiloparsec arm, was discovered in the 1950s and provided some of the first evidence that the Milky Way had a bar. The 3 kiloparsec arm isn't a spiral arm in the traditional sense, but a region where gas has been compressed by the gravitational influence of the bar, creating a dense lane of shocked material. Beyond the immediate vicinity of Sagittarius, a star, the central bulge of the Milky Way contains billions of stars, most of them old red giants that formed billions of years ago when the galaxy was young. The bulge is shaped like a peanut or a boxy structure when viewed from the side, the result of the bar's influence over time. As the bar rotates and evolves, it can buckle and puff up vertically, creating this distinctive shape. The bulge is also home to some of the oldest stars in the galaxy, ancient suns that have been orbiting the center for over 10 billion years, witnesses to the Milky Way's entire history. The density of stars in the bulge is extraordinary. If our solar system were located in the bulge instead of out in the quiet suburbs where we actually are, the night sky would be unrecognizable. Instead of a few thousand stars visible to the naked eye, there would be millions. The sky would be so bright with starlight that it would never truly get dark. Planets in such a system would experience constant illumination, and any civilizations that arose there would have a very different view of the universe than we do. They would see the galaxy from the inside, surrounded by stars in every direction, with no clear view of the spiral arms or the outer regions. But they would also face challenges. The density of stars increases the likelihood of close encounters, gravitational disruptions that could destabilize planetary orbits, or even fling planets out of their solar systems entirely. Radiation levels would be higher, with more supernovae, more stellar winds, and more high-energy particles flooding the region. It's unclear whether life could easily develop and survive in such an environment. Perhaps our location, far from the chaos of the galactic center, is not just a random accident, but a prerequisite for the kind of stable, long-lived planetary system that allows life to evolve. The supermassive black hole at the center of the Milky Way is not unique. Nearly every large galaxy in the universe appears to have one, with masses ranging from millions to billions of times the mass of the Sun. The existence of these black holes raises profound questions about how galaxies form and evolve. Did the black holes form first, seeding the growth of galaxies around them, or did galaxies form first, and the black holes grew later by swallowing gas and stars? The answer is still unclear, but observations suggest a deep connection between the mass of a galaxy's central black hole and the properties of the galaxy itself, particularly the speed at which stars in the bulge are moving. This relationship, known as the M-sigma relation, hints that black holes and galaxies grow together, influencing each other's evolution over billions of years. Sagittarius, a star, has been quiet for a long time, but it wasn't always this way. There's evidence that in the past, perhaps just a few million years ago, the black hole was much more active, devouring large amounts of material and emitting powerful radiation. structures called the Fermi bubbles, two enormous lobes of high-energy gamma rays, extending 25,000 light-years above and below the galactic plane, may be the remnants of a past outburst from the black hole. These bubbles, discovered in 2010 by NASA's Fermi Gamma Ray Space Telescope, suggest that Sagittarius, a star, experienced a violent episode, perhaps triggered by the infall of a massive gas cloud or the disruption of a star that sent shock waves and radiation rippling outward through the galaxy. The bubbles are still glowing today, a faint echo of that ancient explosion. In the future, Sagittarius, a star, will continue to sit at the center of the galaxy, pulling in occasional gas clouds and stars, flaring briefly when something gets too close, and slowly, very slowly, growing more massive over time. In about 4 billion years, when the Milky Way collides with the Andromeda galaxy, Sagittarius, a star, will meet its counterpart, the supermassive black hole at the center of Andromeda, which is even more massive at around 100 million solar masses. The two black holes will spiral together over hundreds of millions of years, eventually merging in a cataclysmic event that will release gravitational waves so powerful they'll ripple across the universe. The resulting black hole will be a true giant, the anchor of a new merged galaxy that will dominate the local group. For now, the beast at the heart of the Milky Way sleeps, a 4 million solar mass monster lurking in the darkness, surrounded by millions of stars and clouds of superheated gas, pulling everything toward it with a gravity so strong that even light cannot escape. It's a reminder that at the center of our home, at the point around which everything rotates, there is not light but darkness, not creation but destruction, a void that devours everything that comes too close. And yet, without it, the galaxy as we know it might not exist. The black hole helps shape the structure of the Milky Way, influences the flow of gas and the formation of stars, and anchors the entire system in place. It's both a threat and a foundation, a beast and a guardian, the hidden heart of the galaxy that built us, Geopatu. The Milky Way is not a quiet place. It's not a peaceful collection of stars sitting still in the darkness, slowly aging and fading away. It's alive with motion, energy, and forces that shape everything within it. There are winds blowing through space, shock waves rippling through clouds of gas, rivers of charged particles streaming along invisible highways, and vast bubbles of superheated plasma expanding outward from the galactic center like the breath of a sleeping giant. This is galactic weather, a term that might sound strange at first, because we think of weather as something that happens in atmospheres, with rain and wind and storms. But the galaxy has its own version, operating on scales so vast and time scales so long that they dwarf anything we experience on Earth. And underlying all of this, holding it together, guiding the flow of gas and the birth of stars, is something we can't see with our eyes, but can detect with specialized instruments: the magnetic field of the Milky Way, a cosmic skeleton made not of bone, but of invisible force that threads through the entire galaxy like veins through a body. Magnetic fields are everywhere in the universe. Earth has one, generated by the swirling motion of molten iron in its core. The Sun has one, created by the churning of plasma deep inside and extending far out into the solar system. And galaxies have them too, vast magnetic fields that stretch across thousands of light years, woven into the fabric of the interstellar medium, the gas and dust that fills the space between stars. The Milky Way's magnetic field is remarkably strong for something spread across such enormous distances. Near the Sun, the average strength of the total magnetic field is about 6 microgauss, which sounds tiny compared to Earth's magnetic field of about 0.3 Gauss. But when you consider that this field stretches across the entire galaxy, the total energy contained in it is staggering. In denser regions, like the spiral arms, and especially near the galactic center, the field strength increases. In the central region of the galaxy, the magnetic field reaches 20 to 40 microgauss, and in the dense clouds of cold molecular gas where stars are born, it can reach several milligauss, strong enough to influence the collapse of gas clouds and the formation of new stars. The origin of these galactic magnetic fields is still debated, but the leading theory is that they're created by dynamo processes, the same kind of mechanism that generates Earth's magnetic field. In a dynamo, mechanical energy, the movement and rotation of conducting material like plasma or ionized gas, is converted into magnetic energy. In the Milky Way, the rotation of the galaxy, combined with the turbulent motions of gas clouds and the outflows from supernovae and stellar winds, all contribute to building and maintaining the magnetic field. Over billions of years, what might have started as a weak, tangled field becomes organized, stretched, and amplified by the galaxy's rotation and the continuous injection of energy from stars. The structure of the Milky Way's magnetic field is complex. It's not a simple dipole, like Earth's, with a north and south pole. Instead, it follows the spiral arms, wrapping around the galaxy in long curved lanes that mirror the distribution of gas and stars. The field is mostly parallel to the plane of the galactic disk, threading through the spiral arms and the regions between them. But it's not uniform. There are reversals, places where the direction of the magnetic field flips, pointing in the opposite direction. One major field reversal has been confirmed in the disk, at a galactic radius inside the location of the solar system. This means that as you move inward toward the center of the galaxy, the magnetic field changes direction, a feature that has profound implications for understanding how the galactic dynamo works. Measuring the magnetic field of the Milky Way is incredibly difficult because we're inside it, and because magnetic fields are invisible to normal telescopes. Astronomers use several clever techniques to map the field. One method involves observing the polarization of light from distant stars. When starlight passes through dust grains aligned by the magnetic field, the light becomes polarized, oscillating in a preferred direction. By measuring this polarization, astronomers can infer the direction of the magnetic field along the line of sight. Another method uses radio waves emitted by pulsars, the rapidly spinning remnants of massive stars. As the radio waves travel through the magnetized interstellar medium on their way to Earth, they experience Faraday rotation, a phenomenon where the plane of polarization rotates, depending on the strength and direction of the magnetic field. By measuring how much rotation has occurred, astronomers can map the magnetic field in 3 dimensions with much higher resolution than is possible for other galaxies. In 2012, an international team led by the Max Planck Institute for Astrophysics created the highest precision map of the Milky Way's magnetic field ever produced. Using over 41,000 measurements from 26 different radio astronomy projects, the map revealed not only the large-scale structure of the galactic magnetic field, but also small-scale features that provide information about turbulence in the galactic gas. The map showed complex patterns, regions where the field is strong and organized, and regions where it's tangled and chaotic, reflecting the dynamic nature of the interstellar medium. The magnetic field plays a crucial role in shaping the galaxy. It's not just a passive feature, but an active participant in the life cycle of stars and the structure of the galaxy itself. Magnetic fields provide support to gas clouds, preventing them from collapsing too quickly under their own gravity. They also help transport angular momentum, allowing gas to lose its spin and spiral inward, feeding star formation, and eventually funneling material toward the supermassive black hole at the center. In regions of active star formation, magnetic fields can channel the outflows from young stars, creating the bipolar jets and outflows that are commonly observed around protostars. The field can also trigger the formation of stars by compressing gas clouds and creating regions of higher density where gravity can take over. In 2024, the Event Horizon Telescope collaboration revealed a new image of Sagittarius A star, the supermassive black hole at the center of the Milky Way, this time in polarized light. The image showed strong, twisted, and organized magnetic fields spiraling from the edge of the black hole, strikingly similar to the magnetic field structure observed around the much larger black hole at the center of the galaxy M87. This discovery suggested that strong magnetic fields might be common to all black holes, and that they play a critical role in how black holes interact with the gas and matter around them. The magnetic fields near Sagittarius, a star, may also be responsible for launching jets of particles, though no such jet has been definitively observed from our galaxy's central black hole yet. The similarity to Me-87, which does have a massive jet, hints that Sagittarius, a star, might have a hidden jet that's simply too faint or pointed in the wrong direction for us to see. Beyond the magnetic field, the Milky Way is filled with other forms of galactic weather. One of the most dramatic structures is the Fermi bubbles, two enormous lobes of high-energy gamma rays that extend 25,000 light-years above and below the galactic plane. Discovered in 2010 by NASA's Fermi Gamma Ray Space Telescope, these bubbles are invisible to optical telescopes, but glow brightly in gamma rays, the highest energy form of light. The bubbles are roughly symmetrical, bulging outward from the galactic center like two massive balloons. Their edges are sharp and well-defined, suggesting they were created by a sudden, violent event rather than a slow, gradual process. The leading theory is that the Fermi bubbles are the remnants of a past outburst from Sagittarius, a star, perhaps triggered a few million years ago when the black hole swallowed a massive gas cloud or disrupted a star. The energy released by that event would have sent shockwaves rippling through the gas around the black hole, heating it to millions of degrees and accelerating particles to near light speed. These particles, mostly electrons and protons, would have been flung outward along magnetic field lines, creating the vast structures we see today. The Fermi bubbles are still expanding, though very slowly, and they're still glowing with the energy of that ancient explosion. Inside the bubbles, the gas is hot, thin, and filled with high-energy particles known as cosmic rays. These cosmic rays are mostly protons and atomic nuclei that have been accelerated to nearly the speed of light. They travel along the magnetic field lines, bouncing back and forth between regions of stronger and weaker field strength, a process known as magnetic mirroring. As they travel, they emit gamma rays through interactions with the gas and magnetic fields, creating the glow we detect. The Fermi bubbles are not the only signs of past violence from the galactic center. There are also structures called the Rosetta bubbles, detected in X-rays by the German space telescope Rosetta. These X-ray bubbles are even larger than the Fermi bubbles, extending out to nearly 40,000 light-years, and they may represent an earlier, even more powerful outburst or a different phase of the same event. The existence of these bubbles tells us that the Milky Way's center has not always been as quiet as it is now. In the past, it was much more active, perhaps resembling the active galactic nuclei we observe in other galaxies, where supermassive black holes are actively feeding and pumping enormous amounts of energy into their surroundings. Galactic winds are another form of weather in the Milky Way. These are streams of gas and particles that flow outward from regions of intense star formation or from the galactic center, driven by the combined effects of supernovae, stellar winds, and radiation pressure from massive stars. When a massive star explodes as a supernova, it releases an enormous amount of energy in a matter of seconds, more than the sun will emit in its entire lifetime. This energy heats the surrounding gas to millions of degrees and drives it outward at speeds of thousands of kilometers per second. When many supernovae explode in a relatively small region, their combined energy can blow a hole in the galactic disk, creating what's called a superball, a cavity of hot, low-density gas surrounded by a shell of cooler, denser material. These superballs can grow to hundreds of light years across, and in some cases, they can break through the disk entirely, allowing hot gas to escape into the halo above and below the plane of the galaxy. This process, known as galactic fountains, helps recycle material between the disk and the halo, enriching the halo with heavy elements created in stars and bringing fresh gas back down to fuel new generations of star formation. The Milky Way breathes, inhaling gas from the halo and exhaling hot, metal-enriched gas back out into space. Cosmic rays, the high-energy particles accelerated by supernovae, magnetic fields, and other violent processes, are another crucial component of galactic weather. These particles travel through the galaxy at nearly the speed of light, interacting with gas, magnetic fields, and radiation. When cosmic rays collide with atoms in the interstellar medium, they can create showers of secondary particles, including gamma rays, which is one way astronomers detect cosmic rays, even though the particles themselves are electrically charged and get bent by magnetic fields, making it impossible to trace them back to their sources. Cosmic rays play an important role in the energy balance of the galaxy and in the chemistry of the interstellar medium. They can ionize atoms, creating charged particles that interact with magnetic fields and influence the dynamics of gas clouds. They can also heat the gas, preventing it from cooling and collapsing too quickly. In some regions, the pressure from cosmic rays is comparable to the pressure from gas and magnetic fields, making them a significant factor in the structure and evolution of the galaxy. The interstellar medium itself is a complex multi-phase environment. It's not a uniform sea of gas, but a mixture of hot and cold, dense and diffuse regions, each with its own properties, and each playing a role in the life cycle of stars. The hot ionized medium, with temperatures of millions of degrees, fills much of the volume of the galaxy, but contains relatively little mass. It's created by supernovae and stellar winds, and is the medium through which galactic winds and cosmic rays travel. The warm neutral medium and warm ionized medium, with temperatures of thousands to tens of thousands of degrees, fill the spaces between denser clouds and are where much of the gas resides. The cold neutral medium, with temperatures of only tens to hundreds of degrees, is found in dense clouds where stars are born. These clouds are threaded with magnetic fields that help support them against collapse and guide the flow of gas within them. Some of the densest and coldest regions, known as molecular clouds, are the birthplaces of stars. These clouds can be hundreds of light years across and contain enough gas to form thousands or even millions of stars. The magnetic field in these clouds is crucial. It provides support against gravity, preventing the clouds from collapsing too quickly, but it also allows gas to flow along the field lines, feeding the regions where stars are forming. The interplay between gravity, magnetic fields, and turbulence determines where and how quickly stars form, and it's one of the most active areas of research in astrophysics. All of these processes, the magnetic fields, the cosmic rays, the galactic winds, the superbulls, the Fermi bubbles, the multi-phase interstellar medium, are interconnected. They form a complex system of galactic weather that shapes the Milky Way on every scale, from the smallest dust grains to the largest structures spanning tens of thousands of light years. And underlying all of it is the invisible magnetic skeleton, a network of field lines that threads through the entire galaxy, guiding particles, shaping clouds, and connecting the past, present, and future of the Milky Way in ways we're only beginning to understand.
据我解剖
Beyond the bright spiral disk, beyond the glowing bulge, beyond the spiral arms where new stars are born, there lies a region that most people never think about when they picture the Milky Way. It's a vast, nearly invisible shell of stars that surrounds the entire galaxy like a ghostly cocoon, stretching out hundreds of thousands of light years in all directions. This is the stellar halo, and it's not a place of creation, but of memory, a graveyard filled with the oldest stars in the galaxy and the scattered remains of smaller galaxies that were torn apart and devoured billions of years ago. The halo is dim, containing only about 1% of the Milky Way's visible stellar mass, but it holds secrets about the galaxy's violent past, a past written in the motions and compositions of stars that have been orbiting the galactic center since the universe was young. If you could see the Milky Way from the outside, the halo would appear as a faint spherical glow surrounding the bright disk, populated by ancient stars and dense clusters of stars called globular clusters. These globular clusters are some of the most spectacular objects in the galaxy, dense balls of hundreds of thousands or even millions of stars packed into a region only tens of light years across. From a distance, they look like fuzzy smudges, but close up, they're a chaotic swarm of stars so tightly packed that if you lived on a planet inside one, the night sky would be filled with thousands of stars brighter than Venus, casting shadows and illuminating the darkness. The Milky Way has about 150 to 200 known globular clusters, though more are likely hidden behind the dust and gas of the galactic disk, or lurking in the outer reaches of the halo, where they're too faint to detect. These clusters are incredibly old, most of them over 12 billion years, formed when the universe was less than a billion years old, and the Milky Way was just beginning to take shape. The stars in these clusters are ancient red giants and dim white dwarfs, stars that have exhausted their nuclear fuel and are slowly fading away. They're also metal poor, a term astronomers use to describe stars that contain very little of the elements heavier than hydrogen and helium. In astronomy, everything heavier than helium is called a metal, even though most of those elements, like carbon, nitrogen, and oxygen, aren't actually metals in the chemical sense. The reason halo stars are metal poor is simple. They formed at a time when the universe was still mostly made of hydrogen and helium, the primordial elements created in the Big Bang. The heavier elements, forged in the cores of stars and scattered by supernova explosions, hadn't yet been produced in large quantities. So the first generations of stars, the ones that formed the halo, were made almost entirely of light elements. As the galaxy aged and more stars lived and died, they enriched the interstellar medium with metals, allowing later generations of stars, like our Sun, to form with much higher metal content. The halo stars tell a story of a time before the Milky Way as we know it existed, a time when the galaxy was still assembling itself from smaller pieces, and those pieces, those smaller galaxies that merged together to form the Milky Way, left their fingerprints all over the halo. In the early 2000s, astronomers made a startling discovery using data from the Sloan Digital Sky Survey, a massive project that mapped the positions, colors, and brightnesses of millions of stars. They found that the halo was not smooth and uniform, but filled with streams, clumps, and overdensities, regions where stars seemed to cluster together in long ribbons that wrapped around the galaxy. These structures were the remnants of dwarf galaxies that had been torn apart by the Milky Way's gravity, their stars scattered along their orbital paths like breadcrumbs, marking the trail of a cosmic collision. One of the most dramatic examples is the Sagittarius dwarf elliptical galaxy, a small galaxy that's currently in the process of being cannibalized by the Milky Way. Discovered in 1994, the Sagittarius dwarf is located on the far side of the galactic center, about 70,000 light-years from Earth. It contains only a few tens of millions of stars, making it tiny compared to the Milky Way, which has hundreds of billions. But the Sagittarius dwarf has a distinction. It's the closest known satellite galaxy to the Milky Way, and it's being ripped apart before our eyes. As the Sagittarius dwarf orbits the Milky Way, the larger galaxy's gravity pulls on it, stretching it out and stripping away its stars. These stars don't disappear. They spread out along the dwarf galaxy's orbit, forming a long stream that wraps around the Milky Way multiple times, like a ribbon wound around a ball. Astronomers have traced this stream across more than 360 degrees around the sky, a complete loop that shows just how thoroughly the Sagittarius dwarf has been shredded. Over the next few billion years, the remaining stars of the Sagittarius dwarf will be completely absorbed into the Milky Way's halo, and the dwarf galaxy will cease to exist as a separate object. It will become just another layer in the fossil record of the halo, a ghost of a galaxy that once was. The Sagittarius dwarf is not alone. The Large and Small Magellanic Clouds, the two most prominent satellite galaxies of the Milky Way, visible as faint smudges in the southern hemisphere sky, are also slowly being consumed. The Large Magellanic Cloud is about 160,000 light-years away and contains about 30 billion stars. The Small Magellanic Cloud is slightly farther and smaller, with around 3 billion stars. Both galaxies are irregular in shape, lacking the spiral or elliptical structure of larger galaxies, and both are surrounded by streams of gas and stars that have been pulled away by the Milky Way's gravity. Recent studies have shown that the Magellanic Clouds are likely on their first approach to the Milky Way, meaning they haven't completed a full orbit yet, but they're not going to escape. The gravitational pull of the Milky Way will eventually drag them in, and over billions of years, they too will be torn apart and absorbed. In fact, the Magellanic Clouds are already interacting with each other, with gas and stars flowing between them in a structure called the Magellanic Bridge. The interactions between these two galaxies and the Milky Way are creating disturbances in the halo, ripples and waves that can be detected in the motions of stars and the distribution of gas. In 2022, astronomers announced that they had detected a massive wave in the disk of the Milky Way, a vertical ripple that extends across thousands of light years and affects millions of stars. The leading theory is that this wave was caused by a close pass of the Sagittarius dwarf, or the Magellanic Clouds, millions of years ago, their gravity stirring up the disk like a hand dragging through water. The wave is still moving through the galaxy, a lingering echo of an ancient collision, but the Sagittarius dwarf and the Magellanic Clouds are just the most recent victims. The halo is filled with the remains of much older mergers, collisions that happened billions of years ago, when the Milky Way was still young. One of the most significant of these ancient mergers was discovered in 2018 using data from the Gaia satellite, a European space mission that has measured the positions and motions of over 1 billion stars with unprecedented precision. Astronomers noticed that a large population of stars in the halo had unusual orbits. Instead of moving in the same direction as the rest of the galaxy, these stars were moving in the opposite direction, on retrograde orbits that brought them plunging through the galactic disk. This was a clear sign that these stars didn't originate in the Milky Way, but came from a separate galaxy that merged with ours billions of years ago. The intruder was named Gaia Enceladus, after the giant from Greek mythology, though it's also sometimes called the Gaia sausage, because of the elongated shape of the orbits of its stars. Gaia Enceladus was a dwarf galaxy, larger than the Sagittarius dwarf, but still much smaller than the Milky Way, with a mass of a few tens of billions of solar masses. Around 10 billion years ago, it collided with the Milky Way in a violent merger that shook the entire galaxy. The collision didn't just add stars to the halo, it also thickened the disk, heated up existing stars, and may have triggered a burst of star formation in the inner regions of the galaxy. The stars from Gaia Enceladus are now scattered throughout the halo, but they can still be identified by their unique chemical compositions and their distinctive orbits. Chemically, they're slightly richer in metals than other halo stars, suggesting that Gaia Enceladus had undergone more star formation before the merger, enriching its gas with heavier elements. This chemical fingerprint allows astronomers to trace which stars in the halo came from Gaia Enceladus and which came from other sources, like the Milky Way's original halo or other, smaller mergers. Since the discovery of Gaia Enceladus, astronomers have identified several other ancient merger events, each leaving its own signature in the halo. These include the Helmi stream, a group of stars moving together through the halo that likely came from a dwarf galaxy that merged with the Milky Way about 6 to 9 billion years ago, and Sequoia, another possible dwarf galaxy remnant that collided with the Milky Way even earlier, perhaps 11 to 12 billion years ago. There's also Tamnos, Arjuna, Itoi, Nyx, Icarus, Pontus, and others, each named after mythological figures, and each representing a galaxy that once existed independently, but is now nothing more than a scattered collection of stars orbiting the Milky Way. Some of these structures are controversial, with astronomers debating whether they represent true merger events or just statistical fluctuations in the distribution of halo stars. But the overall picture is clear. The Milky Way didn't form in isolation. It grew by eating other galaxies, absorbing their stars, gas, and dark matter, and building itself up over billions of years through a process called hierarchical assembly. In the current model of galaxy formation, known as lambda cold dark matter, or lambda CDM, galaxies form from the bottom up. Small clumps of dark matter collapse first, pulling in gas that cools and forms stars, creating the first dwarf galaxies. These dwarf galaxies then merge together to form larger galaxies, which merge to form even larger ones, and so on. The Milky Way is the product of countless such mergers, a patchwork quilt stitched together from the remnants of hundreds or perhaps thousands of smaller galaxies. The halo is the fossil record of this process, preserving the evidence of mergers long past in the orbits and compositions of its stars. The study of these merger events is called galactic archaeology, and it's one of the most active fields in astronomy today. By analyzing the chemistry and kinematics, the motions of halo stars, astronomers can reconstruct the history of the Milky Way, figuring out when different mergers happened, how big the merging galaxies were, and what impact they had on the Milky Way's structure and evolution. The Gaia satellite has been revolutionary for this work, providing the precise measurements needed to disentangle the complex web of orbits and identify stars that belong to specific merger events. In 2023, a comprehensive study using data from the APOGEE spectroscopic survey and Gaia examined the chemical properties of various halo substructures, including Heracles, Gaia Enceladus sausage, the Helmi stream, Sequoia, Tamnos, Aleph, LMS-1, Arjuna, Itoi, Nix, Icarus, and Pontus. The study found that most of these substructures have chemical properties that match those of dwarf Milky Way satellites, like the Sagittarius DS, confirming that they're the remnants of cannibalized dwarf galaxies. However, Nix and Aleph were found to be chemically similar to disk stars, implying that these substructures were likely formed in situ within the Milky Way itself, rather than being accreted from outside. The study also found that Arjuna, LMS-1, and Itoi have chemistry indistinguishable from Gaia Enceladus, suggesting they may all be part of the same merger event, just different pieces of the same shattered galaxy. The halo also contains a small number of stars that are moving so fast they're escaping the galaxy entirely. These hypervelocity stars, traveling at speeds of hundreds of kilometers per second, were likely ejected by gravitational interactions with the supermassive black hole at the galactic center, or by the disruption of binary star systems in close encounters with other stars. Some hypervelocity stars may also be former members of dwarf galaxies that were flung out during the merger process. Wherever they came from, they're now on one-way trips out of the Milky Way, destined to wander the intergalactic void forever. In 2022, astronomers discovered that the shape of the Milky Way's stellar halo is not spherical but Zeppelin-shaped and tilted relative to the galactic disk. This unexpected geometry suggests that the halo is still carrying the imprint of ancient merger events, its shape distorted by the infall of dwarf galaxies that didn't come in along neat, symmetric orbits, but from random directions. The tilt of the halo may also be influenced by the dark matter halo, which could itself be lopsided or misaligned with the disk. The study of the halo and its substructures is revealing the Milky Way to be not a static, unchanging object, but a dynamic system that has been shaped by billions of years of collisions, mergers, and gravitational interactions. Every star in the halo has a story, a history that stretches back to the early universe, when galaxies were smaller, closer together, and more prone to violent encounters. And the process is not over. The Milky Way is still eating galaxies, still growing, and in about 4 billion years, it will undergo its most dramatic merger yet, when it collides with the Andromeda galaxy. That collision will scramble the disk, fling stars into new orbits, and create a new, larger halo filled with stars from both galaxies. The graveyard will grow, filled with the ghosts of two great spirals that once dominated the local group, but are now united in a single massive elliptical galaxy. The halo is a reminder that nothing in the universe lasts forever, and that the Milky Way we see today is just one moment in a long, violent, and ongoing story of cosmic cannibalism. Belief that Earth was the center of everything, to the humbling realization that we are passengers on a small planet orbiting an ordinary star in the outer suburbs of a galaxy that is itself just one of trillions in the observable universe. It took the collapse of the geocentric worldview, the heresy of Copernicus, the courage of Galileo facing the Inquisition, the mathematical precision of Kepler, and the genius of Newton to finally understand that Earth moved, that the sun was not unique, and that the stars were distant suns scattered across unimaginable distances. It took the development of new technologies, radio telescopes that could hear the whispers of hydrogen gas, infrared observatories that could see through the dust, space-based telescopes that could peer into the galactic center without the interference of Earth's atmosphere, to finally unveil the spiral structure, the bar at the center, the warped edges, and the hidden skeleton of magnetic fields that thread through the entire galaxy. It took decades of watching individual stars whip around the galactic center at impossible speeds to prove that a 4 million solar mass black hole lurked at the heart of the Milky Way. And it took the global collaboration of the Event Horizon Telescope to finally capture an image of that black hole, a glowing ring of light surrounding a dark shadow, the signature of a region where gravity is so strong that not even light can escape. Every discovery built on the ones before it, each generation of astronomers standing on the shoulders of giants, pushing the boundaries of what we could see and what we could understand. And what have we learned? We've learned that the Milky Way is not a simple static object, but a dynamic evolving system shaped by billions of years of violent history. We've learned that the galaxy is a cannibal, that it has spent its entire existence devouring smaller galaxies, tearing them apart and absorbing their stars into its halo, leaving behind streams and shells and ghostly remnants that are still visible today, if you know where to look. We've learned that the Sagittarius dwarf is being shredded right now, stretched into a long ribbon of stars that wraps around the entire galaxy, and that the Magellanic clouds are on a death spiral that will eventually bring them crashing into the Milky Way billions of years from now. We've learned that the halo is filled with the remains of ancient mergers, galaxies like Gaia and Enceladus that collided with the Milky Way 10 billion years ago, and left their chemical fingerprints in the stars that now orbit in retrograde paths through the galactic disk. We've learned that the Milky Way has not one disk, but two, a thin disk filled with young stars, gas and dust, and a thick disk populated with older stars, both of them warped at the edges and rippling with waves triggered by past collisions. We've learned that the galaxy has a bar, an elongated structure of stars stretching through the center that acts like a conveyor belt, funneling gas inward toward the core and feeding bursts of star formation. We've learned that the supermassive black hole at the center, Sagittarius a star, is surprisingly quiet right now, but wasn't always, that a few million years ago it may have erupted in a violent outburst that created the Fermi bubbles, two enormous lobes of high-energy gamma rays extending 25,000 light-years above and below the galactic plane, structures so vast they dwarf the entire visible disk. We've learned that the galaxy has weather, winds blowing through space at thousands of kilometers per second, shock waves rippling through gas clouds, cosmic rays streaming along magnetic highways, and superbulls carved out by the combined fury of multiple supernovae. We've learned that the Milky Way has a magnetic skeleton, an invisible network of field lines that guides the flow of gas, supports collapsing clouds, and shapes the structure of the galaxy on every scale from the smallest dust grains to the largest spiral arms. We've learned that most of the galaxy's mass is not in stars or gas or dust, but in dark matter, an invisible substance that we can only detect through its gravitational pull. But that makes up roughly 85 to 90% of the galaxy's total mass, forming a vast halo that extends 3 times farther than the visible disk and holding everything together with its gravity. We've learned that the Milky Way is not alone, that it's part of the Local Group, a collection of over 50 galaxies dominated by the Milky Way and Andromeda, and that it's on a collision course with Andromeda, our larger sibling galaxy, that in about 4 billion years, the two will begin to merge in a slow-motion train wreck that will take hundreds of millions of years to complete, scrambling both galaxies, flinging stars into new orbits, triggering bursts of star formation as gas clouds collide, and eventually merging the 2 supermassive black holes at the center into a single giant black hole that will anchor the new merged galaxy. We've learned that our location in the galaxy may be part of the reason life exists on Earth, that we're in a kind of galactic Goldilocks zone, not too close to the chaotic radiation-flooded center where close encounters between stars would destabilize planetary systems, and not too far out in the metal-poor outer regions where the heavy elements needed to build rocky planets and complex molecules might be too scarce. We're in the Orion Spur, a quiet branch between 2 major spiral arms, about 26,000 light-years from the center, orbiting at over 500,000 miles per hour in a slow, graceful circle that takes 230 million years to complete. We're moving, always moving, carried along by the rotation of the galaxy, but the motion is so smooth and constant that we never feel it, just like we don't feel the Earth spinning beneath our feet or racing around the sun. But perhaps the most important thing we've learned is how much we still don't know. We don't know what dark matter is, whether it's made of exotic particles or something else entirely, whether we'll ever be able to detect it directly, or whether it will remain forever invisible, known only by its gravitational effects. We don't know how supermassive black holes form, whether they grow slowly by swallowing gas and stars, or whether they were born massive in the early universe. We don't know exactly how many spiral arms the Milky Way has, with different studies proposing different numbers, depending on how you define an arm. We don't know the full history of the galaxy's mergers, how many dwarf galaxies have been absorbed over the billions of years, what each one contributed to the Milky Way's structure and evolution. We don't know how common life is in the galaxy, whether Earth is an anomaly or whether the Milky Way is teeming with life on countless worlds, some of it simple, some of it complex, some of it perhaps even technological and aware of the same stars we see. We don't know if we'll ever be able to leave our tiny corner of the galaxy and explore the rest of it, whether humanity will spread to the stars or remain confined to a single solar system for the entirety of its existence. These unknowns are not failures, they're invitations, challenges for future generations, reminders that the universe is vast and full of mysteries waiting to be solved. The Milky Way has been revealing itself slowly, piece by piece, over thousands of years, and there's no reason to think that process will stop. Every new telescope, every new mission, every new technique for analyzing starlight or detecting gravitational waves or mapping the motions of distant objects brings us closer to understanding the full story of our galactic home. The journey from ancient myths to modern astrophysics is a testament to human curiosity, to our refusal to accept easy answers, to our willingness to question authority and challenge deeply held beliefs in the pursuit of truth. It's a journey that required patience, courage, and collaboration across generations and across cultures, each contributing their piece to the puzzle. And it's a journey that's far from over. The Milky Way is not just our address in the universe. It's the crucible where we were forged, where the elements in our bodies were created in the cores of stars and scattered by supernovae, where the gas clouds that collapsed to form our solar system were shaped by galactic winds and magnetic fields, where the conditions were just right for a stable planetary system to form and for life to take hold, and eventually evolve into beings capable of looking up at the night sky and asking where we came from and where we're going. We are not separate from the Milky Way. We are part of it, made of its matter, shaped by its history, moving with its motion, living in the narrow window of time when it's an active, star-forming spiral galaxy before it merges with Andromeda and transforms into something new. This is our moment, our place, our cosmic context, and understanding it changes everything. It changes how we see ourselves, not as the center of creation, but as one small part of something vastly larger and older and more complex than we ever imagined. It changes how we see our planet, not as an isolated world, but as a rare and precious oasis in a galaxy that is mostly empty space, a tiny blue marble where the conditions happen to be just right for life. It changes how we see the stars, not as distant, unchanging lights fixed on a celestial sphere, but as suns like ours, each one potentially surrounded by planets, each one born from the same clouds of gas and dust that formed our sun, each one destined to age and die and return its material to the galaxy, to be recycled into new generations of stars. And it gives us perspective on time, on the fact that the galaxy is over 13 billion years old, that it was already ancient when our solar system formed 4.6 billion years ago, that it will continue long after the sun has burned out and the Earth is gone, that galaxies live and die and merge and evolve on timescales so vast they make human history seem like the blink of an eye. The pale band of light that ancient peoples saw and wondered about is still there, still visible on dark nights, far from city lights, still arcing across the sky like a bridge between worlds. But now we know what it is. It's the combined light of billions of stars, the edge on view of the galactic disk, the glow of our cosmic home seen from the inside. And every time we look up and see it, we're seeing across time, seeing the light from stars thousands of light years away that left those stars long before recorded history began, seeing the structure of a galaxy that took billions of years to build, and that's still changing, still evolving, still eating smaller galaxies and growing, still forming new stars and killing old ones, still spinning through space at incredible speed, carrying us with it on a journey that began in the early universe and will continue until the stars themselves go dark.